based, and Manish Kumar is based as well. So I was born somewhere in the south of Italy. Then I moved north of Italy where I did my master degree in Ferrara, 2011. Then I moved to Oxford in 2014 when I was like first associate professor, first assistant professor, then associate professor like 2 years ago. This is a bit some glimpse about Udine. It's a nice city, small city, not very crowded, very calm. Sometimes not very exciting as well. But it's a nice place to live. It's very close to the Alps. These big mountains, chain of mountains surrounding the north of Italy. So you can see some beautiful landscapes, some rivers. This is Cividale del Friuli, where you can do the arts. Okay, residual stress. The residual stress is very narrow. The magnitude is very high. Okay. And if for some reasons you have a defect, you have a porosity, you have an inclusion or whatsoever, I find it very, very interesting. It's a human aorta, it's a blood vessel, it's one of the biggest. And essentially, this is, for me, it's super fascinating because you can clearly see this is an aorta after that has been removed. So there is no blood, and there is no blood pressure actually. What happens is that the inner layer gets buckled, okay? Why is that? Because nature basically thought that if we introduce some compressive residual stress in the inner part, okay, the aorta could resist these some concept of types of residual stress. So essentially, point-wise, in a specific point, the residual stress can be identified as the sum of these three types of residual stress. So another nice recent paper from some people in Italy and US where they try to resolve residual stress in the depth using essentially using some regularization methods, and they end up saying that if your regularization, I'm talking about 1 by 1 millimeters, you can resolve single grains and you can resolve type 2 residual stress as well with this technique, which is super powerful and it's been developed like very recently. If you have an SEM equipped with an EBSD detector in your lab, then you can also try to perform HR-EBSD. Okay, you explode and rotate it. You can extract some information about elastic strain. Okay, and essentially you, in principle, can reconstruct a full tensor if you know the elastic properties, so you go from strain to stress. That's very helpful. What is the drawback? What is the limitation of non-destructive techniques? Non-destructive techniques essentially have, if you exploit the focus ion beam, it's a technique that cuts material at micron scale. You might perform some slits, then you, with digital image correlation, so you keep acquiring images of the surface, and then you can track the deformation of the material. Okay. Some people use, well, all of them, they use finite elements then to reconstruct the go back and reconstruct the residual stress that has been relieved. Another technique which I contributed a lot during my PhD was the ring core method. Essentially, it relies on the same principle, a different location within a ring. And as I said, you can also get depth profiling, and also this alpha here represents the principal direction. So you can also get the principal direction from this technique. Good. Great. From the modeling point of view, there are some techniques that can be exploited. For example, multiscale and finitization and some other mechanical mechanisms, and you end up with some maps of residual stress. And also some other methods which are not related to type 2 and type 3. They refer to type 1 residual stress. It's called eigenstrain reconstruction method, and basically this method allows you to enforce the information of the residual stress that you get experimentally by constraining using the balance, the compatibility, Okay, you enforce these experimentally evaluated values and distribution so that you can check whether you're doing it right. And this is particularly useful when you deal with the non-destructive methods, where you don't know at the absolute value, but by introducing eigenstrength concept, then you can actually, it's very helpful to get reliable results. Then you can use the information that you got from residual contains and residual stress. So the neighboring material also contains residual stress, and by playing with the sign of the residual stress inclusion, you can actually divert the crack. Okay. This might be very useful, maybe for designing new materials. Okay. Because of course, if you divert the cracks, then you need more energy, so the overall fracture toughness of the material increases. And this is something that Manish Kumar is doing at the moment. So we are employing residual stress in polycrystalline materials. This is a very brief clip of cantilever that, and we are actually modeling intergranular and intragranular fracture using phase field. So fatigue, we all know fatigue. This is very general, I'm not talking about stress, talking about strain, so it includes the point where you have the actual fatigue phase. It's very important if you want to include information of residual stress to understand which regime of fatigue you're dealing with. Why? Because if you're dealing with low cycle fatigue, you are here, and I'm pretty sure you have seen some ductile fracture or low cycle fatigue fractography images. You see that in the crack initiation points, well, there are actually crack initiation points, not a single one. So the damage is kind of diffuse. You might have different points where the crack okay. While for high cycle fatigue and very high cycle fatigue, you can either have, most of the times, most of the mechanical components have cracks that start from the surface, free surface. That's because the material can slide, can undergo this shear. So you have extrusion, intrusion, so it's more free to move, so it's more likely to have crack starting from the free surface. Recently, we're dealing with additive manufacturing, and additive manufacturing have porosity inside, they have big pores, and in some cases, essentially, no matter how rough or not rough the surface is, you might have fatigue crack initiation from the bulk of the material. This is the work we have done on low cycle fatigue to understand the role of residual stress. We have seen that you have this distribution in this dog bone shaped material of residual stress, axial, radial, and hoop. And we have seen that only after a few cycles, the residual stress that is there gets wiped out. Okay? It floods out. So yes, you can have residual stress, is there, but in low cycle fatigue, very few cycles, because you undergo plastic deformation and the residual stress basically disappears. Okay? As you can see, after 5 cycles, then 200 cycles, 300 cycles, essentially you have the same level. What about high cycle fatigue? You might know that there are several methods to assess fatigue in high cycle and very high cycle fatigue, essentially mostly high cycle fatigue. Theory of critical distance, strain energy, implicit gradient, strain field, many others. All of them rely on the knowledge of a specific characteristic length, okay? In which, for example, if we have a notch, we do our stress analysis, we have the gradient of stress around the notch. People, what they do, essentially, they define a characteristic length, like for the critical distance theory, as you define a distance and you pick the stress at that distance. Or with the strain energy density, you define an area or a volume and you make an average. You average the strain energy on a certain volume or surface. So essentially, what we're dealing with is an evaluation that is averaged over a certain domain, and this certain domain is linked to a certain length, so a characteristic length. Okay. What we have seen also in the literature is that this characteristic length, the control radius, is called here, changes throughout the life. So if we're dealing to nearly low cycle fatigue, you have a characteristic length. As you move towards the very high cycle fatigue, you have different characteristic length. Okay. So, and this of course then leads us to understand how and why and when we need to introduce residual stress in our fatigue prediction and evaluation. So essentially, if we are dealing with very high cycle fatigue, we are here, our control radius is around 0.02, so 20 micron, okay? So if we want to introduce residual stress in this regime, we need to resolve residual stress with this resolution, okay? If we're then dealing with low cycle fatigue or like nearly low cycle fatigue, we don't need that much resolution, okay? So essentially, we have to play. We have to play with different length scales if we want to take into account this effect. Okay, statistical approaches. So essentially, you have the distribution of different sides. What I would like to do in the future is I would like to explore these approaches also for residual stress. So I would like to get some statistical information at different length scales, so type 1, type 2, type 3, and I would like to get this information. Okay, you have a systematic shift of the mean stress. So the first thing that we look at is the high diagram or Schmidt-Doppler diagram. There are several, and this is a generalized one, so you have different lines for different number of cycle levels. Okay. If we consider our material, which we apply a certain stress amplitude, then we have the mean stress. The mean stress is actually our residual stress, but our residual stress, this is type 1, sigma m star, but if we want to introduce the multi-scale problem, then this is no longer, we need to give it more information. What is this more information that we need? Is essentially how this value is spread, okay? So what is the statistical distribution of this value? At a given like length scale of reference. Then if we can exploit that, then we can say what is the probability of having a mean stress at a specific location. We decide the confidence level, and then we can make our assessment. Okay. So this is an approach that I would like to pursue in the future, and is based basically on probabilistic approaches. Conclusion and future developments. So nowadays there are several experiment techniques that are becoming more and more reliable, and some more are being developed. This is a very exciting field, let's say. There are several numerical methods for crystal plasticity. People talk about molecular dynamics, well, DFT have several numerical methods which you can deal with residual stress, and I think they are very helpful. It is evident that the choice of appropriate reference length scale depends on the fatigue damaging mechanism, and also therefore to the fatigue regime. And this is something maybe it's more subjective, but I think one way to account for the stress in the future, talking about like 10 years, 20 years from now on, is to approach a problem with probabilistic method. I would like to acknowledge all the people that worked with me in the past more than 10 years from facilities in the UK, in Italy, and my current research group, because of course these are the people who do the hard work, and they must be acknowledged. So Manish Kumar is professor, and 2 postdocs and some PhD students. I would like to highlight some PhD opportunities in my group, because I got awarded a good project, a European project ERC, essentially dealing with the topics I've been talking about today. So there will be at least one PhD studentship available in the next month in several topics. So underlying topics are related to that project. So the effects, multiscale residual stress, physics, machine learning with physics informed, paradigms, crystal plasticity, structured process modeling, H-field, residual methods. I also work on metamaterials using some shape memory materials and of course welding technologies. For those who might be interested in, we opened a new course, master's course in Italy about industrial engineering for sustainable manufacturing. This is because Europe is pushing a lot towards sustainable matters and renewable topics. So we would like to teach and prepare future engineers to deal with these important topics. And this course is not trivial to say, but it's entirely taught in English. In Italy, we don't do that often. So courses essentially are taught in Italian. Good. Thank you for listening to me. I think I took more time than I was allowed to, and I hope you enjoyed. And I'm open for any questions. Quite fast in the last part, but I hope it's okay.
So it's fine. So questions?
Like
Monotonic or like fatigue?
Fatigue.
Yeah, it's residual stress is very important because you have every time you apply a load, then you have plastic deformation around the crack tip, and this plastic deformation.
Context is also if you are considering like whether it is safe to go in that direction, like considering constant resistance.
Well, you should look at I've seen some maps, but to be honest now I don't know how the residual stress distributes in a ray, right? Because you always have like some regions where you have compressive and some tension, right? If, for example, the
various component of residual stress like two stresses, radial stress and axial stress. Then how can we decide that which stress is more harmful in case of the
for pressure vessels. I mean, you need to understand what is the residual stress that is introduced by the manufacturing processes. But generally, I would say I'm not an expert in a pressure vessel, at least from